Rift basins. Consider a layer of the crust or lithosphere and which is under an extension. So, it can produce conjugate normal fault, what can be called as a graben structure, and a depression is produced. This basin can be called as a rift basin. This is a case of a full graben. We can also develop a half graben structure where a single normal fault is involved. Rift basins are extremely important to study. Its structure stratigraphy is very important because many hydrocarbon reserves are associated with these rift basins. What causes rifting? There are two views. One says that there is tectonic stress which is extensional, leads to the formation of a rift basin. The second view is that due to magmatic push, a rift basin can be created. For example, here is a lithospheric layer and a magma body is pushing, trying to move upward. So, it will produce an extension in this direction and the basin can be produced. Below a rift basin, usually igneous rocks are found. In fact, there is a debate whether due to the push of the magmatic material the extension happens, or since there is a crustal stretching induced by tectonic movement and extension, the igneous material moves upward. Which one is the cause, which one is the effect, egg or chicken, which came first becomes a question. Is it that due to the extension of the crust rifting happens and as an effect magmatic material moves up, or is it that due to magmatic material moving up crustal extension happens? We will come across a term post-rift magmatism in the discussion. After rifting, sometimes magmatism has been documented in many of the rift basin. We call that as the post-rift magmatism. Let us not link the post-rift magmatism with this magmatic materials moving upward. This magmatic material that moves upward is not related with post-rift magmatism. In fact, this is the precursor of rifting. We can find out terms such as magma rich rift basin and magma poor rift basin, but poor does not mean that magma is completely absent. Two other terms are to be understood: the meaning of the term passive rifting and the active rifting. Passive rifting is characterized by passive asthenospheric upwelling. That means the asthenosphere moves passively, not actively, and in response to overlying layers separation controlled by regional tectonic extension. So, if here is a layer and we are pulling it, primarily due to this tectonic extension, a rifting has developed, and as a result here the asthenospheric material has moved up. Such a rifting is called as the passive rifting. In contrast, what is active rifting? It is characterized by active asthenospheric upwelling. In case of passive rifting, asthenospheric material moved up passively, whereas in case of active rifting, the asthenospheric material moves up. As it moves up, the lithosphere is stretched in two directions, leading to a rifting known as the active rifting. The detail can be found over here, the tectonic region, and one can consult this book for other detail. Rift basins are favorable places of hydrocarbon reservoirs worldwide. Now, the exact rift basin stratigraphy will vary from one rift basin to another. The stratigraphy is dependent on the topography that is created by tectonics. When the rifting is happening, if any deposition happens, we call it syn-rift sedimentary deposit, syn-rift succession, syn-rift phases. The deposition occurs while subsidence continues within a basin defined by either as a full graben. I have already explained the concept of full graben or half graben. Now, here is an example where normal faulting has happened at one place and in the other place. Here the net slip is more for this normal fault. So, this part is the deepest part of the basin, and the deepest part receives the maximum sedimentation. So, this is also the eventually the thickest sediment deposition. The pre-rift rocks can be marked and we can call it as a basement, which is here. Close to the steep fault, we find fan delta conglomerates. This is the zone of shales and the distal turbidites. At the top lies the deltaic deposits and the shoreline sands. This is the deltaic deposit and the shoreline sand. Note the lithological contacts, they are not sharp but zigzag in geometry. So, also here we call these geometries as tongues. So, from here one can find out succession of a syn-rift facies distribution. This is an ideal situation. Each rift basin will have some variation. In the rift basin, the potential reservoirs are abundant in syn to post-rift sedimentary rocks. Syn-rift sedimentary rocks I am going to discuss, post-rift sedimentary rocks also I am going to discuss. And what are the reservoir rocks? They are commonly sandstones and also sometimes they are carbonates. Seals are an important part to have hydrocarbon reservoir which are of low permeability, and they are common in the post-rift successions. We do not find seals in the syn-rift succession, and they are widespread in the marine syn-rift successions. A few terms to be understood: sag basin and passive margin. What is a sag basin? This one, which is figure A here. They are the broad shallow depression formed within a continental landmass or a craton due to slow subsidence. In the diagram, it is a shallow deposition. Shallow with respect to what? I am going to discuss the passive margin deposit, where there is much more thickness clearly visible in the diagram. So, compared to the passive margin deposit, the sag basin deposits are considerably shallow depressions and there is less accumulation of sediment. Therefore, they are formed within a continental landmass or craton. Cratons or shields are the tectonically stable parts of the earth's crust where these sag basins can develop, and they are formed due to slow subsidence. Subsidence is the reason of their formation. And what is their geometry? In plan, they can be circular, elliptical, etc., and they are marked by sedimentation for a very long time. On the other hand, passive margin is a transition zone between continental and oceanic lithosphere, and that is not an active plate boundary. What are the different facies that can be seen? The deep water, more basinal deposits can be seen at the bottom of the sag deposit. It can also be seen in a part of the passive margin deposit. The contact between the deep water deposit and the shallower deposit in case of a sag basin is almost horizontal, whereas here in case of a passive margin it is zigzag, lenticles are produced. So, overall we can say it is a near vertical contact, although it is zigzag. The fluvial deposits form the topmost layer of the sag basin, whereas the fluvial deposits are found in a passive margin from the shallowest part up to some extent in the depth. So, here vertical succession has not developed, important. One can find the deltaic deposits, it can be located over here, and the deltaic deposits are found over here. The syn-rift sediments and the post-rift sediments can be distinguished in this ideal diagram. This is the normal fault at the two boundaries of the basin, and this is the sense of movement. When the faulting was happening, sedimentation took place and that got ended over here. So, this portion constitutes the up to this much syn-rift deposit, and when the rifting has stopped, further layers have come into existence, and this can be called as the post-rift deposit. Now, the source rock for hydrocarbon can be found within the syn-rift sediment, and it can also be found within the post-rift sediments. The white colored portion, that means over here, is the pre-rift rock. Before rifting, these rocks were there. and that rock of course got faulted. An idealized syn-rift sediment stratigraphic column is presented here. The column is divided into 3 stages: stage 1, stage 2 and stage 3. Different symbols are provided here. The overbank shell can be found within stage 1, not in stage 2 and in stage 3. They are laminated overbank shells. Fluvial sandstones can be found in stage 1, also in stage 3. The lacustrine shell, a very thick deposit found within stage 2, and deltaic and shoreline sandstone can be found as the topmost unit in the stage 2. So, based on what I have discussed, write down the stratigraphic succession based on the rock names for stages 1, 2 and 3. Note, we are talking here about the syn-rift stratigraphic column, which means we are talking about this portion, we are not talking about the post-rift deposition. Is there any pre-rift deposition? No, it is not possible, because if there is no rifting, there is no depression, so no sedimentation is possible. Pre-rift deposition not possible to discuss as such, but the pre-rift rocks, even if you consider it is sedimentary, will be in this portion and will be called as such as pre-rift rocks. To understand the post-rift basins and the deposition, we have to first understand the meaning of the term thermal subsidence of a basin. What it is? It is a sinking of the earth's crust due to cooling. In rift basin, initial heating and thinning of the lithosphere are followed by a period of cooling and subsidence. Consider close to the lithosphere a magma body has come. So, this is the place of intense heating and extension. Now, the basin has developed, syn-rift sedimentation has happened, and after that, when this material has cooled, the basin starts subsiding. That means, this package of material subsides. When this subsidence happens, further sedimentation happens, and that is known as the post-rift sedimentation. Post-rift facies, post-rift sedimentary rock, etc. can be said. That is what is said here. The post-rift basins either contain strata that are deposited during thermal subsidence following rifting in case of a sag basin, or are broad depressions extended laterally over large area than the underlying fault bounded syn-rift basins. Note this term, laterally over a larger area than the underlying fault bound deposits. This is the extent of the syn-rift sedimentation that happened, and in case of a post-rift deposition, the areal extent is much more. This is a general statement well applicable for the rift basin, and it can be understood from common sense. What is the statement? For a given amount of extension, high angle faults can lead to more subsidence. A measure of extension is heave, a measure of subsidence is throw. Let us try to understand. Consider here is a normal faulting, and I am watching in a vertical section. So, I can understand that this point has come over there. So, if I draw a vertical line and a horizontal line, this horizontal distance is the extension and is known as heave, the horizontal component of the net slip, and here throw is the vertical component of the net slip, which is given by T. Now, the dip of the fault theta is given by tan inverse T divided by H, which means that as theta increases for a constant H, T increases. You can also make such statements as theta increases for a constant T, what happens to H. Say this is a faulted unit, this is T and this is H, and this is the dip of the fault theta. Consider a steep dipping fault theta, you can see that T has increased, H has reduced. Now, coming to this statement, for a given amount of extension, that means for a given amount of heave H, high angle faults can lead more subsidence. As you see here, if the fault is high angle, then the unit undergone more subsidence, and that is indicated by is higher throw. And from this statement, you can write the converse statement also. For a given amount of extension, low angle faults lead to less subsidence for a given amount of extension H, if H is fixed. We are going to see two rift basins from India, the Barmer basin in Rajasthan located in western India. The two bounding faults for the Barmer basin are shown here. They are the normal faults, and inside them are several normal faults understood geophysically, and from several studies such a succession has been established which involves also the tectonic phases, stratigraphy in terms of the structures. As you can see the diagram, the normal faults are shown and also the formation names are given. We have a Precambrian basement which is a Malani igneous shoot, over which is a lower Jurassic Lathi formation, and then comes a Mesozoic deposition, Cretaceous, Paleogene, and then the Neogene succession. This research paper compiles the stratigraphy of the Barmer basin from so many sources, and it is summarized in this table. The basement is of Malani shoot of igneous rocks. Then significant deposition is found in the Cretaceous, then Paleocene, then in the Paleogene, Neogene, and the Quaternary desert sand deposition. My question to the students is, can you locate here the syn-rift deposition based on this concept, stage 1, stage 2 and stage 3? Are you able to locate stage 1 deposits, stage 2 deposits and stage 3 deposits, or are you getting some other pattern? Look at this succession where the structural geology has been told. Look at this succession also where the rock types are told and the ages are told in this succession. Are you able to locate any post tectonic deposition in the Barmer stratigraphy? You may or may not be able to get, but the answer should be backed with arguments. We are now going to see the Jaisalmer basin, another basin from Rajasthan, India. This is the map and the different lithologies are shown, the formation names are given. These are the deposits of the Jaisalmer basin. The stratigraphic succession of this basin was compiled by these authors. This is a very detailed succession, and we actually start from here, from the basement, and then after this gets over, move to this succession, and after this gets over, then come to this succession and consider this. After this gets over, then this is the final topmost succession. Recent is over here, that means the recent deposition of loose sand and the alluvial material. Again, this succession is compiled from these authors and many other authors not shown here, but my question is, noting the rock names, probably facies detail you will also find, or you can work out, you will find out the ages of rocks, such as these ages are shown continuously, they have been described. Are you able to locate the syn-rift and the post-rift deposits? Now, this may or may not be possible in case of the Jaisalmer basin and the Barmer basin, but I just wanted to give you a flavor of real stratigraphic succession, so that you understand how far the ideal succession deviates from the real succession. Further, a question, what are the similarities and difference in successions of the Barmer and Jaisalmer basin? Just point out those similarities and find out the differences. Is it that the Mesozoic rocks in the Barmer and Jaisalmer basin are similar, are they same, or are they different? What about the igneous activities within the Barmer basin? Are we getting post-rift magmatism, any evidence in the Barmer basin in the succession, or are we getting any magmatic evidence in the middle of the succession of the Jaisalmer basin? Let us look at the post-collisional stratigraphy in the collisional mountains such as the Himalaya, taking an example of the Shivalik portion. Shivalik Himalaya deposits have been described as a molasse deposit. As the mountain moved up to a great height, rocks were rapidly eroded and they got deposited in the ancient foreland basin, the foreland basin of the past, the present day designated as the Shivalik region. This white portion here represents the Indo-Gangetic plain, which is not a part of the Himalaya. This yellow portion is the Shivalik region. The boundary between the Shivalik and the Indo-Gangetic region is the main frontal thrust. Northeast of the Shivalik region lies this green region, which is the Lesser Himalaya. The boundary between the Shivalik and the Lesser Himalaya is the main boundary thrust, MBT. This is the Indian city Dehradun. Close to Dehradun, one can locate the main boundary thrust, where the northeast portion of it is the Lesser Himalaya and the southwest portion of this is the Shivalik Himalaya. We are going to see the Shivalik Himalayan stratigraphy from Tripaঠি's compilation in 1986. The lower Shivalik rocks consist of the Kamlial formation, the Chinji formation. The middle Shivalik rock consists of the Nagri formation and the Dhokpatan formation. Between middle Shivalik and upper Shivalik rock lies a disconformity. Within the upper Shivalik rock, the bottommost formation is the Tatrot formation, then comes the Pinjor formation, and then the boulder conglomerate units. Let us look at the lithology. In the Kamlial formation, it is consisting of sandstones and shells. I am not getting into the fossil detail. In the Chinji formation, we have sandstones and shells. In the Nagri formation, we have got sandstones and shells. In the middle Shivalik, in the Dhokpatan formation, we have sandstones and clays. In the Tatrot formation, where the first glaciation took place, we have coarse grained, usually soft sediment sandstones with interspersed conglomerate, and then comes the Pinjor formation, where we have got silts, sand and clay units, and then comes the boulder conglomerate. As the name indicates, dominantly there are conglomeratic bodies. The variation, the total range of the Shivalik group we can write as mid-Miocene to mid-Pleistocene. This is the history of sedimentation. When the Himalaya was rapidly rising at mid-Miocene, it attained such a height that in this package of sediments. Now, once you visit any of these locations, by the way, most of the type locations are in Pakistan, or also if someone visits the Indian Himalaya for field work, one may find conglomerate bodies here, here, here. The question is that the upper Shivalik's boulder conglomerate? The answer is no. Rivers that are flowing are also bringing conglomerates from the top. That is not the boulder conglomerate unit. In the succession from lower Shivalik to middle Shivalik to upper Shivalik, we do not see any limestone, no carbonates, and we get clastic sediments. One can also look at the ancient foreland deposit of the other collisional mountains such as Alps, Andes and Zagros, and try to correlate what are the common and uncommon factors in the ancient foreland deposits of these collisional orogens. While looking at the layered rocks in the collisional belt, ophiolite needs a mention. What are ophiolites? They are the fragments of oceanic lithosphere that are produced at spreading centers at oceanic ridges, back arc basins or forearcs during subduction initiation. The oldest ophiolite is the Zunhua ophiolite in the eastern China. The age is 2550 million year. Ophiolites are layered rocks. They did not become geographically widespread until around 900 million year, and after around 900 million years, several ophiolites are found. Possibly why the younger ophiolites are more found? They are because they are better preserved, or due to an increasing global network of interconnected plates. Let us look at an ophiolite succession. We have at the bottommost unit crystalline shield with overlying platform of sedimentary sequences. Then as one moves up, tectonic with or without sedimentary melanges, that means random mixture of rocks associated with imbricate slices of marginal sediments. As one moves up, one finds metamorphic complexes, commonly 0 to 100 meter thick, that means very thin to thick varieties are possible, shown by this color, over which lies the ultramafic tectonite, peridotite and discontinuous layers of dunite, and it can have the chromite deposits. As one moves up, one can find ultramafic materials, felsic at the top, these rocks. Further up, one finds a massive non-cumulate plutonic rocks with diorite, plagiogranite, and intrusive breccias. Then there comes a transition zone, then comes further younger the dike complex. From the dike complex, as one moves up, there is a transitional contact. We do not get a sharp contact of pillows and massive lavas. Pillows indicate igneous activity in contact with water, over which lies the pelagic sediments or the abyssal deep sea fan, which can be terrigenous deposits or arc type deposits, over which lies an unconformity, that means a time gap, over which lies the shallow water or continental deposits commonly with laterites. This is a succession of ophiolite. In not all the ophiolites we can get chromite. In all ophiolites we may not get each and every units that have been referred. There can be few additional rock types. Where are they produced? In the collisional mountain. To explain that, I am taking you to the Indian example of ophiolite. Just as one example, I am going to show the Nidar ophiolite complex. Note that the word complex has been used. This is in the Ladakh, that means in the Trans-Himalaya. And here we get almost a complete succession from uppermost mantle material to the marine pelagic sediments at the top, the uppermost mantle succession at the bottom. This is the map of India. This is the portion that we are talking. This is the location Chumuthang, Nyoma, Mata, that is Somorari Lake. This is the place Nidar. The rock types and the stratigraphic units are demonstrated by color code. So, this is one such place in Trans-Himalaya in the collisional belt where we get such a succession of ophiolite. Note that there has been considerable debate with the term of ophiolite and what should be the definition, and I have tried to provide a definition which is as latest as possible, not getting into the historical development of the concept of the ophiolites.